IPM, Interior Permanent Magnet Motor, Part 2, Open Circuit Calculation. Let's take a moment to remind ourselves where we are in the series of videos. Having completed a preliminary design of a 10 kilowatt induction motor, in the previous video we replaced the rotor by an interior magnet rotor to begin the design of an IPM. So here we see the cross-section of the rotor and the stator together. We're planning to use the same winding configuration, but we may decide to change the number of turns. The stator is otherwise unchanged from the induction motor, but the original specification is again summarized here at lower left. All the preliminary dimensions have been decided, but we've not yet chosen the magnet material. So let's do that now by choosing a neodymium ion boron material with a remanence of 1.13 Tesla and a relative recoil permeability of 1.024. This is not a definite commercial grade of magnet, although it is close to many. It is actually towards the lower end of the Neo family and towards the upper end of the samarium cobalt family. But since we're concentrated on the design procedure, we don't need to consider these details too closely at this stage. It might be worth noting that there is room for maneuver by using a higher or lower grade of magnet depending on requirements. Now, the first thing I would like to do is to assume that the magnets have been successfully magnetized and inserted in the rotor, and run a finite element calculation to look at the magnetic field before the rotor is inserted into the stator. The reason for this is to underline the fact that these rotors require very careful handling in the factory. Even out in the open, the field is strong enough to attract ferromagnetic objects. Field gradients are very high, not only in the radial direction but also around the rotor. And not only that, but the direction of the field changes rapidly as we move around the region surrounding the rotor. As anyone who has worked with this type of rotor will know, this means that any ferromagnetic object can easily be wrested from one's grip and smash itself against the rotor surface with violent force, quite possibly causing permanent damage if it strikes one of the bridges, and there's also a danger of personal injury. Here, some of the field components are plotted as a function of angle around the rotor just to underline the rapid variation in the shape and strength of the field. The numbers in brackets are radii normalized to the rotor surface. The highest value is about 0.45 Tesla, just outside the bridges. Although this doesn't sound high compared to the flux densities inside the machine, you would certainly feel it as a very strong field with a steel probe such as a screwdriver. And again, before we get down to business, here is another unusual finite element calculation in which the rotor is inserted into a keeper. That is a close-fitting steel tube that constitutes a magnetic shunt or short circuit around the entire rotor. What this does is to remove almost all the magnetic reluctance in the magnetic circuit so that the magnets operate close to the remnant flux density. The magnetic short circuit is not quite complete because of the clearance gap. But we can see that with a flux density of 1.06 Tesla in the magnets, they are operating at about 94% of the remnant flux density. In days gone by, some motorcycle alternators and bicycle lighting dynamos were built with permanent magnet rotors using Alnico magnets with low coercivity, and it was necessary not to withdraw the rotor from the surrounding stator without sliding it into a keeper. Otherwise it would lose a large fraction of its magnetization. Fortunately, this is not necessary with high coercivity magnets such as those we use today. But even so, a keeper is still an interesting accessory if the rotor has to be removed and stored safely for any length of time. I'm not suggesting that the finite element calculations in the last couple of slides are particularly important for the designer, but I think they do help us to get a better feel for the nature of a magnetized rotor. Later, we will pay a little closer attention to the actual operating point of the magnets on their demagnetization characteristic. Now we really do come to the serious business of calculating the open circuit field with the rotor inserted in the stator. This is the JMAG model. Of course, only one quadrant is needed because of symmetry. Actually, we could reduce the solution domain to only one octant, but the full quadrant is probably a better view. Easier to interpret because we don't need to double or halve anything or conduct mirroring exercises in the mind's eye. We can see all the features of the field of one pole. We can see the expected saturation in the bridges, where the flux density reaches about 2.2 Tesla, and in the central web, where it reaches about 2.1 Tesla. We can also see the effect of the stator slots, which produce dips in the air gap field. Under the teeth, the air gap flux density reaches about 0.85 Tesla, and in the stator teeth we see a peak flux density of about 1.3 Tesla, and also in the yoke we see a similar peak flux density of about 1.3 Tesla. This shows the radial component of flux density in the middle of the air gap plotted over one pole pitch, that is 90 mechanical degrees, from minus 45 to plus 45 mechanical degrees, centered on the d-axis. We can see again the peak flux density of about 0.85 Tesla under the teeth and the severe dips caused by the slotting. These dips are surprisingly large. The fundamental space harmonic component is responsible for the fundamental time harmonic component of the EMF, and here it is calculated by Fourier series with a peak value of 0.8396 Tesla. Also shown in the graph is the ideal theoretical flux distribution, which is rectangular and spans the pole arc angle, which we can see in slide 9, alpha 60 degrees mechanical degrees or 120 electrical degrees from this point to this one. The rectangular distribution can be calculated approximately using the well-known magnetic circuit method, and we've summarized here a few of the key equations which can be found in chapter 3 of the Green Book, which is now 11 years old. I might mention that the precursors of the Green Book were published in 1989 and again in 1993 by Oxford University Press, but the methods are much older and go back to the 1950s. We still maintain errata for all these books as a matter of academic duty, so please email if you would like a copy, or if you find any more errors. The working of the current numerical example will be available in a further textbook later this year, so it's not intended to repeat all the details, but the result in this case is remarkably close to the finite element calculation with a peak flux density, fundamental flux density, of 0.8396 Tesla. It's worth pointing out a few details. The clearance gap is dealt with by the artifice of an equivalent magnet whose properties are given by these two formulas, where nu equals C over Lm, the ratio of the clearance gap to the magnet length in the direction of magnetization. When this ratio is small, let's say less than 0.1, the equivalence is very good. And here we have nu equals 0.0555 or 1/18. So we can safely rely on this simplification. The formula for the total flux per pole, phi g, comes directly from the magnetic equivalent circuit model, where PM0 is the permeance of the magnet and Rg is the reluctance of the air gap, and little p RL is a normalized linear leakage permeance which accounts for flux leaking in parallel with the web and the bridges when they are heavily saturated. The remnant flux of the magnet Br nu Am is depleted by subtracting the leakage fluxes in the web and the two bridges before being introduced into the rest of the magnetic equivalent circuit. This formula treats the saturated web and the two bridges as flux sources in the opposite direction to the magnet itself, so they have the effect of wasting some of the magnet width directly. If the magnet remnant flux density is, let's say, 1 Tesla, and the bridge and the web saturate at 2 Tesla, then for every millimeter of width in the web plus bridges, we will lose the flux from twice that number of millimeters in the magnet width. And here the combined width of one web and two bridges is 3 plus 2 times 1.4, that's 5.8 millimeters. So we're going to lose the flux from approximately 11.6 millimeters of magnet width. And since the overall magnet width is only 2 times 28.7 millimeters, that loss represents over 20% wastage of magnet. That is a shocking figure, especially in view of the high cost and scarcity of rare earth magnets. We will return to have a closer look at this issue in the video, a little bit later in the video. Fourier series analysis of the rectangular distribution is very simple, and the resulting fundamental flux per pole is phi m1 5.766 milliwebers. It might be of interest to compare this with the figure we had for the induction motor, which was 5.494 milliwebers per pole. So the IPM is giving us about 4.95% more fundamental flux per pole on open circuit. At this point, we are ready to determine the stator winding. We can begin with the same winding layout that we used in the induction motor. That is a three-phase lap winding with 36 coils. There are 4 coil groups per phase. Each group comprises 3 lapped coils, and this defines the so-called phase spread as 3 slot pitches, which is 3 times 10 mechanical degrees, or 3 times 20 equals 60 electrical degrees, a common configuration. In the induction motor, the number of turns per coil was 17. But since the flux per pole is 4.95% higher than that of the induction motor, we can reduce the number of turns per coil to 16. So 16 divided by 17 multiplied by 1.0495 equals 0.9878. So we can expect a slightly lower EMF and a slightly higher current. With 16 turns per coil, the number of turns in series per phase is 16 times 2 groups in series in each path, and 3 coils in series in each group. So we have 96 turns in series per phase. The winding factor is the product of the pitch factor KP1 0.9848 and the distribution factor KD1 0.9598, that is 0.9452, and with 5.766 milliwebers per pole and a frequency of 93.3 Hz, we get the EMF 216.97 volts RMS. In the next video, we will proceed to the calculation of the synchronous inductances which are necessary for performance calculation. But to end this video, I would like to perform a little study which is concerned with the waste of magnet material mentioned earlier due to the back leakage of precious magnet flux in the central web and the 2 bridges on either side of the pole. In slide 10, we estimated the waste at 20% of the magnet material. The idea is to see how we might remove the web and the bridges. If we are to do that, we must provide some means of holding the rotor together. So here we have the web and the bridges, and here we've removed them. Present, absent. So one way to hold the rotor together would be to encapsulate all the rotor components in a plastic molding. Another way would be to shrink a carbon sleeve over the entire assembly of the magnets and pole pieces in exactly the same way that is done with high-speed surface magnet motors. In either case, we are likely to need a larger air gap than the 0.4 millimeters we started with. So I made a model in JMag with a smooth bore stator that has 2 transition regions on the inside, which can be treated as steel or air. The smooth bore avoids the need to build 2 or 3 more complete models with slots, and the initial air gap of 0.456 millimeters is determined using Carter's coefficient with the original 0.4 millimeter air gap so as to represent the slotting approximately. So in slide 12 we see the flux lines with the web and bridges both present, and in slide 13 they are both absent. We have to be a bit careful with flux lines because the interval of vector potential between any 2 lines, that is, the flux in each tube, is not automatically the same in 2 separate solutions. That's why it's safe to get into the data as soon as possible, and the data I'm interested in here is the operating point of the magnet on its demagnetization curve. This is the familiar demag curve of the magnet, showing the flux density, not the magnetization or polarization. And along the horizontal axis, the magnetizing force in amperes per meter multiplied by mu0, mu0, so that the units are essentially the same on both axes. Why the magnet producers don't use these units, I don't know. They persist in using kilogauss on the axis of induction and Oersteds or amperes per meter on the axis of magnetizing force. But at least these units show the recoil line close to 45 degrees, which makes sense to a machine designer. Now, the recoil line here is not at 45 degrees because of the greatly expanded scale on the axis of magnetizing force. But that's what this is, a recoil line. The knee is way off to the left, or we hope it is, and we're working at a comfortable temperature, not 150 degrees C. Let the operating point fall over that knee, and we're in trouble. So I have 5 cases to consider. The first one, case 1, has the web and both bridges present. And for good measure, I have also closed up the clearance gap by replacing that 0.35mm layer with steel. And that gives me the highest possible operating point in terms of the actual flux density of the magnet, shown by this black square marker at 1.0685 Tesla. The numbers on the dashed lines are the so-called permeance coefficient. And in this first condition, case 1, the permeance coefficient is 17.8, very high. The remnant flux density of the magnet is at 1.13 Tesla. And to go to that point, we would need to surround the magnet by infinitely permeable material with no air gap. And of course it would be perfectly safe in there, but also perfectly useless. There's also another set of markers lower down, and these represent the average flux density around the air gap, so they give an idea of the generated EMF. For case 1 we have 0.543 Tesla. Now let's consider the interesting step from case 1 to case 2. What we're doing is removing the web and the bridges without changing anything else. The average flux density in the air gap increases to 0.654 Tesla, a remarkable increase of about 20%. And that's funny because in slide 10 we estimated the waste of magnet material at the same figure, 20%. So there seems to be some sort of magical correlation. If we look at the magnet operating point in case 2, we find that it has not deteriorated very much. The magnet flux density has fallen to 1.057 Tesla, a drop of only about 1%, while the permeance coefficient has fallen from 17.8 only to 14.8, still high. We can say that the web and the bridges tend to raise the permeance coefficient, while at the same time they lower the air gap flux, because they are in parallel with the magnet and so they divert flux from the air gap. They actually tend to protect the magnet from the demagnetizing influence of the air gap and the reluctance of the remainder of the magnetic circuit in series with the magnet. But while we're here, let's have a look at the effect of the clearance gap, case 3. If we change the 0.35mm layer from steel to air, the air gap flux density falls from about 0.654 to 0.619 Tesla, about 5.5%. The magnet flux density falls from 1.057 to 1.001 Tesla, about the same percentage drop. And that's consistent with the theory of the equivalent magnet, which we mentioned earlier, and which is described on page 165 in the Green Book and elsewhere in the public domain literature. But now we must confront the realities of mechanical engineering. Having removed the web and the bridges, we must now find a way to hold the rotor together. So let's imagine we could do it with a carbon sleeve or Kevlar banding of 1 mm radial thickness to give us a total air gap of 1.456 mm, case 4. The air gap flux density falls to 0.573 Tesla, which is still 5.5% higher than the 0.543 Tesla we started with in case 1, when we were wasting 20% of the magnet. Here we are not wasting 20% of the magnet by back leakage through the web and the bridges, but we don't get a 20% benefit because we've had to increase the air gap to make room for the carbon sleeve or Kevlar banding. This is the crux of the whole business. What is the trade-off between increased flux on the one hand and the cost and manufacturing difficulties associated with this unusual method of construction? Note that the magnet operating point in case 4 is 0.938 Tesla with a permeance coefficient of 5, which I would say is starting to approach the lower range of recommended values for open circuit operation. Remember that the worst case demagnetization is under load conditions, and maybe under fault conditions, and maybe at an elevated temperature. So there has to be a safety margin in the open circuit operating point at room temperature, which is what we have here. It's not a hard and fast rule, because in the complete design process it's necessary to simulate and calculate all the worst case conditions and then to test them in the test lab. So all we're saying here is that we need to keep an eye on it, because what we're doing, first by removing the protective magnetic short circuits of the web and bridges, and then by increasing the air gap, is all going in a direction of a reduction of the safety margin against demagnetization. So finally, in case 5, we have increased the air gap by another 1 millimeter, and the air gap flux density falls to 0.503 Tesla. So we've actually lost about 7% compared to the original configuration in case 1. The magnet operating point has come down to 0.84 Tesla with a permeance coefficient of only 3.1. So we're definitely entering the range where we are losing in all directions. It's not safe to draw general conclusions from this small study about the wisdom of such a configuration. There's something in the idea, for sure. What appeals to me is avoiding that shocking waste of 20% of the magnet material, although that figure itself is rather arbitrary because it's a consequence of the original choice of the thicknesses of the web and the bridges, and those thicknesses were simply starting values, not the result of any detailed analysis. So I hope the discussion is interesting and the method of looking at these ideas. Thanks for listening.